Hello class, welcome back. Today we want to talk about chemical bonding too. So in chemical bonding too, we want to try to determine the properties of molecules by examining the structure. So that's what we want to try and do. Determine properties by looking at the structure. Properties of a substance depend on the structure. The structure includes many factors: the skeletal arrangement of the atoms, the kind of bonding between the atoms, the shape of the molecule. Let's look at the shape of the molecule called geometry. Molecules are three-dimensional objects. We often describe the shape of a molecule with terms that relate to geometric figures. These geometric figures have characteristic corners that indicate the position of the surrounding atoms around a central atom. In the center of the geometric figure, so you have a molecule, you look at its geometry, and look at the central atom, and look at the electrons or the molecules that are around the central atom. The geometric figure also have a characteristic angle, and we're going to call that the bond angles. Lewis theory and molecular geometry. Lewis theory predicts there are regions of electrons in an atom. The regions of electron groups should repel each other. So that's what Lewis theory is predicting. That you have regions of electrons, and these electrons will repel each other. This idea can then be extended to predict the shape of molecules. So we can extend this idea to try to use to predict the shape of a molecule. So I want to talk about the valence shell electron pair repulsion theory. And this valence shell electron pair repulsion theory says that electron groups around a central atom will be most stable when they are as far apart as possible. That's what they're saying. It means they will repel themselves until they are far to each other in such a way that they cannot repel themselves again, then they stop. So at that point now, they give the shape of the molecule. So the resulting geometry arrangement will allow us to predict the shape and bond angles of the molecule. But what are electron groups? We need to understand what electron groups are. Electron groups, what are they? A lone pair of electrons around the central atom is an electron group. Electron in a bond that form a bond is an electron group. But this electron group can be a single bond is one electron group. A double bond is not two electron group, it's one electron group. A triple bond is not three electron group, it's one electron group. So for example, this nitrogen here has three electron groups. You see the lone pair, the double bond, and the single bond. So this nitrogen, this central atom here, has 3 electron groups around it. One lone pair, one single bond, and one double bond. And these electron groups around the central atom determine the geometry of the molecule. So let's examine some of the geometries. Linear geometry is when 2 electron groups are around the central atom. When you have 2 electron groups around the central atom, the result is that the shape of the molecule will be linear. But please, in this case, the electron groups are bonded. And the bond angle will be 180 degrees. Example is beryllium chloride and CO2. You can see their shape. This is linear. This has the single bonds form the electron group, but carbon dioxide is 2 double bonds that form the 2 electron group around the central atom. So carbon is the central atom here. Then beryllium is the central atom here. Trigonal planar geometry. This is when we have 3 electron groups around the central atom. Please, the bonds, the electrons are bonded. And the bond angle is 120 degrees. So example is boron trifluoride. So you see the shape is planar. It's on the plane of the paper. That's why we call it trigonal planar geometry. So we have boron trifluoride, we have boron, we have aluminum, Cl3. These are some examples. Another example is this molecule. So you have, this is H2CO. Bonds are not identical, hence observed angles are slightly different from the ideal. So you have 3 electron group, a double bond, 1 double bond, and 2 single bonds. So this forms a trigonal planar geometry. You can see it here. The bond angles are not perfect because the bond lengths are not the same, they're not identical. But we still have a trigonal planar structure. Tetrahedra. Tetrahedral geometry results when you have 4 electron groups around the central atom. All the electrons are bonded. The bond angle is 109.5. Example is CF4. That's an example. You can have CH42. You can have CBr4. Yeah. These are some examples. So tetrahedral shape is the example. 109, the angle is 109.5. Another example, as I said, is methane. You see, the bonds are the same, so all of them, the bond angles are 109.5. Trigonal bipyramidal geometry. This is when we have 5 electron groups around the central atom. The positions above and below the central atoms are called axial position, and the position in the same base plane as the central atom are called equatorial positions. The bond angles between equatorial position is 120, and the bond angle between axial and equatorial is 90 degrees. So you can see it here. So these are equatorial, 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 and these are axial and axial. Example is PCl5. So you can see these are axial position, and these are equatorial position. This one. Octahedral geometry. This is when 6 electron groups surround the central atom. Bond angle is 90. So this is an example of equatorial geometry. Example is SF6, where you have SCl3. Octahedral geometry. Let's look at the effect of lone pair of electrons. Lone pair groups occupy more space on the central atom, and relative sizes of repulsive forces interaction are lone pair greater than lone pair bonding pair, and lone pair bonding pair greater than bonding pair bonding pair. This repulsion affects bond angles and make them to be smaller. So, derivative shapes. If a molecule has no lone pair and all the bonds are equivalent, the molecule's shape will be one of the basic geometries. So what are the basic geometries? Let's remind ourselves of the basic geometries. I hope you can remember. Let's look. So we have 1, linear. We have 2. So here we have 2 electron pair around the central atom. So this is trigonal, planar, 3 electron pairs around the central atom. Then 3. We have tetrahedral, 4 electron pairs around the central atom. Then we have 4. Trigonal, bipyramidal, 5 electron pair around the central atom. Then we have 5 octahedral. Geometry. So these are the basic geometries, don't forget. But we want to find out the effect of lone pair in any of these basic geometry. Molecules with lone pair or different kinds of surrounding atom will have distorted bond angles and different bond lengths, but the shape will be a derivative of one of the basic geometries. Derivative of trigonal planar geometry. Trigonal planar geometry have 3 electron groups around the central atom. If one of them is a lone pair, the result is that the molecule will have a trigonal bent shape, and the bond angle will be less than 120. Example is SO2. You see, it has this lone pair. This lone pair, one lone pair around the central atom, then 2 of them are bonded. So you have this shape. This is what we call the trigonal bend shape. look at derivative from a tetrahedral geometry. Tetrahedra have 4 electron groups around the central atom. And if one is a lone pair, the result is that we have a trigonal pyramidal, not bipyramidal. Trigonal pyramidal and not trigonal planar. It's trigonal pyramidal shape. Bond angle less than 109.5. Example is NH3 or NCl3 or pH3 or PCl3. You see, phosphorus and nitrogen are in the same group. You can see the lone pair here and the 3 bonded electrons. So look at the shape. This is what we call trigonal pyramidal, not bipyramidal. Trigonal pyramidal shape. Trigonal pyramidal shape. So we can still see it again. These are just the electrons, but we have lone pair. Now you have, this is the actual molecule. You will not see the lone pair when you want to find the shape of the molecule. The lone pair will not be observed. You only see the bonded electrons, the bonds. We are still on tetrahedral geometry. But this time, we have 2 lone pair around the central atom. The bond angle is less than 109.5. And what is the shape of the molecule? It's tetrahedral bent shape. Example is H2O. You have that for H2S also. So bond angle reduces to 104.5. Next, we want to look at trigonal bipyramidal geometry. They have 5 electron groups around the central atom. If some are lone pairs, let's see what geometry will be derived. But the lone pair will occupy the equatorial position because that is where you have more room, more space. So you see, these are axial position. This is axial. And these are equatorial. So you see, they will not occupy this because they don't have more room. They occupy the equatorial position. So let's look at the seesaw shape. 5 electron groups and 1 is a lone pair. You see, this is how it looks like. Glass seesaw. So this is S, F4. Look at this. So that's its shape, you know. This, when you put it this way, it really looks like a seesaw. Looks like a seesaw, you see? T-shape. 5 electron group and 2 are lone pairs. So this is, you see the 2 lone pairs. So that's it. It forms a T-shape. So 5 electron groups and 3 are lone pairs. 3 are lone pairs. 3 are lone pairs. So it gives us a linear shape. That's a linear shape. Let's look at derivatives from octahedral geometry. Octahedra have 6 electron groups. If one is a lone pair, the result is a square pyramidal structure. 6 electron groups and 2 are lone pair. The result is a square planar shape. So square pyramidal shape. So this is so we have just one lone pair. So it gives us a square pyramidal shape. But when we have 2 lone pairs, see the lone pairs? What we have is a square planar. That's a square planar shape. So, in summary, this is summary. Electron groups, bonding groups, lone pair of electrons, the electron geometry, and the molecular geometry that results from that. We can see the bond angles. So look here, you can see the shape on some examples. Look at the shape they form, but look at the examples of the molecules. That continues here too. You see, so the same thing. Continue, you can see the shapes that they have on some examples that we have. Most of these examples we have looked at them. So let's try and use that to answer some problems. Predict the molecular geometry of SiF5-. What you have to do first, you have to draw the Lewis structure. Draw the Lewis structure. So this is the Lewis structure of silicon pentafluoride anion. Then now determine the number of electron groups around the central atom. We can count it 1, 2, 3, 4, 5. It has 5 electron groups around the central atom silicon. 5 electron groups. So use electron group to determine the geometry. We know that when we have 5 electron groups around the central atom, the geometry is trigonal bipyramidal. So that is the molecular geometry for SiF5-. Let's take another example. Predict the molecular geometry and bond angles in ClO2f. The first thing you want to do, you want to draw the Lewis structure. So that is the Lewis structure. Then determine the number of electron groups around the central atom. 1, 2, 3, 4. If you only look at the electron group, you know that is tetrahedral. But you notice we have one lone pair. So if we have one lone pair, what will be the shape of this molecule? So but let's describe what we have seen here. We have 4 electron groups on chlorine. That is 3 bonds and 1 lone pair. So what will be our geometry? It's a derived geometry from tetrahedra. And that derived geometry is trigonal pyramidal. Angle less than 109. Trigonal pyramidal, angle less than 109.5. So on that note, we will have a break and we'll come back to look at how we can draw the 3-dimensional structures of molecules.